Okay, we are going to talk about kinematics, more kinematics, and we're going to talk about motion. Okay, motion in 2 dimension, and this is going to be a motion in a circular path. It's going to be uniform, circular. Okay, circular motion. Okay, what does that mean? Circular motion. Let me do this one better. It's going to be, this is supposed to be a U. Okay, uniform circular motion. Well, what we have here is a particle that's moving on a circle. So here we go. We have our path here, and this is okay, this is our reference here. So we have a particle that's going to move in a circle. So it's going to move like this. And what we have is that we have this point here, and this point here. Oops, this one is not correct. It's right here, right here. It's going to be tangent, has to be tangent, and each one has to be of the same size because the magnitude of the velocity is going to be the same. And what's changing is the direction of the speed. That's what's changing. So what do we have here? We have a vector that goes this way, and that's a velocity vector. And we have a vector that goes this way, and that's a velocity vector. And then we have a vector that goes this way, that's a velocity vector, and a vector that goes this way, and that's a velocity vector. And as you can see, these guys are, this one is going this way, this one is going this way, this one is going this way, and this one is going this way. And as you can see, they all have different directions, but the magnitudes are the same. This magnitude is the same as this one, and this magnitude is the same as this one. Oh, let me make it a little bigger. There you go. So this magnitude is the same. So each one of these vectors, velocity vectors, they have the same magnitude, but they have different directions. And because of that, because they have different directions, they have a centripetal acceleration, which is going to be v to the square over r. So this would be the equation for the centripetal acceleration for a particle that moves in a circular motion. And then you also have the radius. This would be the radius right here, r, 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 and r. So that's your radius. And the speed is constant, but the velocity is changing in direction. That is what's going on here. So we have some equations. We have another equation, which is for the period. And the period is going to be 2 pi r divided by the velocity. And you have this other equation. So you can play around with these two equations. And you can find the centripetal acceleration. For example, let's say that, well, the period is the time that it takes for a trip around the whole circle. If you start here at point A, let's call this point A. So if you start walking at point A and you go all the way around your circle, and depends on how much time it takes to go back to point A, and that would be your period. If it takes you 2 seconds to go back to point A all around, that's your period. If it takes you 5 seconds to go all around your period, all around your circular trajectory, that's your period. So it's the time it takes to go for a full trip all around once. And you measure that time in seconds, and that would be your period. So let's do an example to make this more clear. Let's suppose that the period is going to be 2 seconds. That means that you make a whole trip in 2 seconds. So you start at point A and you walk all the way around and you end up again at point A. So that is your period, and it takes you 2 seconds. And let's say that the radius is going to be 1.5 meters. So that would be the radius. That would be this one right here. This would be your radius, and your radius is constant too. And you want to find the centripetal acceleration. So you got your formula. So you don't have the velocity, but you can solve because the velocity is going to be 2 pi r divided by v period. And then you can plug it here. Over here, I'll do it over here. So acceleration, centripetal acceleration is going to be, well, this is the velocity is going to be 2 pi r. Okay, let's do this one. It's going to be 2 pi r divided by the period, and this is going to be to the square, and this is going to be divided by the radius right here. So what do we got here? We got 4, we got pi to the square, we got r to the square divided by the period to the square, and all this divided by r. And we can plug a 1 here to make this a fraction 2, and then you got another fraction over here. So no big deal there. So you got period to the square times r at the bottom. And upstairs, you can have 4 pi to the square, r to the square. And that's good news because the square gets rid with, it cancels out with the other r. And you end up with 4 pi to the square r. And this is divided by the period to the square. So we can solve this one. Is going to be 4. This is going to be 3.14 to the square, and this is going to be 1.5 meters, and that is going to be divided by the period, which is 2 seconds, and this is elevated to the square. So our centripetal acceleration is going to be equal to, if you do all that math, it's going to be 14.79, and you can see the units. It's meter over second square. So you do have your centripetal acceleration. It's a vector, and it's going to be pointing, let's see, it's going to be pointing towards the center all the time. Let me get a bit better color. Let's use the green. So it's going to be pointing towards the center. So centripetal means towards the center. So it's going to be pointing this way towards the center, right there. And that green vector is your centripetal acceleration. And you have this formula to calculate it. And here is the solution of one problem in 2 dimensions. And this is kinematics, and this is motion in 2D. And this is uniform circular motion, where you have the velocity vector changing in direction, but the speed is the same. And we have solved this problem.